Welcome back, guys. We're going to be looking today at the last section in Chapter 8, which is arc length. And to do that, we're going to go back to Star Wars and check out our old friend Han Solo. So the Kessel Run was a hyperspace route between the Acades Maelstrom, used by smugglers and unscrupulous freighter captains to move spice from the spice mines of Kessel at the behest of the Pike Syndicate, who relied on foolhardy Kessel runs to deliver the illicit substance to their customers. Wow, so go figure. In any case, the Kessel Run is this route that was taken from one place to another. So, what we have here is we're going to say that we are going to go from point K to point S following this route. Okay, and let's see, we're going to travel that route along this parabola, and we need to estimate how long is this route. How long, if they often say that if you put a piece of string on this curve right along it, how long would that piece of string be? And that is arc length. How long is this arc? So we're going to start by estimating how long this arc is going to be by just using the distance formula. So the distance formula gives us the straight line distance between any 2 points, and as anyone, I'm going to have to redo that. Anyone in Algebra 1 will tell you that that's just going to be from the Pythagorean theorem, and it's a difference of x's squared plus a difference of y's squared. So what do we have here? Our difference of x's is 8 minus 0 squared, plus the difference of y coordinates is 8 minus 0 squared also. Okay, so that works out kind of nicely. I suppose we should get a number here for this. Let's go ahead and calculate that. That's 11.3137. Now, this is actually not the path, so that's not that great of an approximation. We can already tell that that's a lot shorter than it needs to be. The true distance is going to be longer than 11.313. But that's okay. This is just a start. Now, another way to do this, using straight line, is to find some point in the middle here and just find the distances between these 2 points and add them together. So we can see that this is already a lot better than our previous estimation. So our distance here is going to be, let's do this first one, that's going to be the square root of 5 minus 0. So 5 squared plus 1.25 minus 0, so 1.25 squared. That's the distance of that first line segment. And then our second line segment, let's change to green. The difference in x coordinates is 8 minus 5, so that's 3 squared, plus, and the difference of y coordinates here, that's 4.5 squared. It's probably a negative 4.5, but when you square it, it won't really matter. So yeah, 12 minus 8 is 4.5. So let's calculate that. That gives me a distance of 16.817. Okay, well, things are going to get crazy now, because now we're going to say if we want an even better estimate, let's just do more line segments. So we're going to do 4 line segments here. Woo! So let's hit it. The first one, the distance in x coordinates, 2 minus 0 is 2 squared. The distance in y coordinates, 8 minus 0 is 8 squared. Now, the second line segment. The distance in x coordinates, 4 minus 2, that's 2 squared. The difference in y coordinates, 12 minus 8, that's 4 squared. So that's our second line segment distance. Our third line segment distance, and we're going to start running out of colors here soon, that's going to be the square root of, now the difference in x coordinates again is 2, so 2 squared, and then the difference of y coordinates, 12 minus 12 is 0 squared. Finally, for our last line segment, the distance in x coordinates, 8 minus 6 is 2 squared, and then the difference of y coordinates, 8 minus 12, that's 4 squared. So as we compute this, I want you to know that it doesn't really matter where we put these other coordinates. As long as they're somewhere along the path, we're guaranteed to get a better estimate, definitely than our first estimate. That all works out to a 19.19048. So we have improved in that we have gotten closer to the actual distance, but notice how our improvement is not as dramatic as the improvement here from 11 to 16. 11 to 16 is a much greater distance than from 16 to 19. So you might think that we're exhibiting some kind of limiting behavior, and you would be right. There is a limit that's going on here to all of these. And as we add more and more points, the limit of all of these distance formulas added together is going to be the actual distance along the straight line, or along the actual curve. So as delta x goes to 0, we're going to get more and more line segments. And if we get more and more line segments and delta x goes to 0, that's calculus. So that's time for our calculus. Let's take a look at what happens here. So we know the distance is going to be the sum of a bunch of distance formulas. Okay? And we're going to do a little bit of algebra here. We're going to factor out a delta x. So delta x squared. Delta x squared times delta x, or divided by delta x squared, is 1. And then delta y squared divided by delta x squared, well, that's just delta y squared on delta x squared. And there's that delta x squared that we had just factored out. Delta x squared gets to leave the absolute, not the absolute value, gets to leave the square root and becomes just delta x. And if we apply the limit now, we're going to say our delta x's go to 0. Well, what happens here? Well, as the limit of delta x goes to 0, you know, this part and this part, those become the integral in dx. But what happens with delta y over delta x as delta x goes to 0? Well, that's just the definition of the derivative. So this delta y over delta x, that becomes dy dx. Over here we can see the limit and the summation becomes an integral. So that actually gives us our formula for arc length. The arc length is exactly equal to the integral of root 1 plus dy over dx squared dx, which probably makes us want to revisit this right over here. And what was my function? It was negative 1/2 x squared plus 5x. Y equals negative 1/2 x squared plus 5x. So dy dx, that's going to be equal to negative x plus 5. And so the arc length here from 0 to 8, x equals 8, that's square root of 1 plus negative x plus 5 squared dx. That's going to be the actual arc length. Let's compute that real quick. Yeah, that's 19.55640. So you can see again the difference here between 4 line segments and the smooth curve is not very much. So, I would imagine if we had, 5 or 6 line segments, our precision would be really close, or would be really, really, really good. Really good. Yeah, good precision. So let's do this one. We got a rainbow modeled by 4 minus x squared from x equals negative 2 to 2. What is the length of this rainbow? Okay, well, the left side of this is x equals negative 2. The right side of this is x equals positive 2. We need dy dx. So dy dx here is the derivative of negative 4x. Sorry, the derivative of 4 minus x squared, which is negative 2x. dy dx squared then is just 4x squared. So going back to my formula for arc length, this is going to be the integral from negative 2 to 2 of 1 plus 4x squared. Now normally with these, if this integrand is not easily simplified, then you're just going to get a calculator to do these, because these integrals get nasty really quick. So I can't make a u substitution because there's no x on the outside to balance the derivative of 4x squared. So I'm just going to use technology. This is equal to 9.29 356 units. So that's all there is to it. Really not a whole lot to finding arc length. Let's get you to your important ideas. We only really had one concept here, and that is the arc length of curved segments. Actually, this will work for straight line segments as well, but the integral is, or the arc length is integral from a to b of 1 plus the derivative squared dx. Now, if you have straight line segments, it's usually easier just to use the distance formula, although I suppose you're welcome to use the arc length formula if you really want to. And if, like I mentioned earlier, technology is often used to evaluate these integrals. Let's finish up here with the Kessel run. So on one particular Kessel run, Han Solo aboard the Millennium Falcon took a path modeled by y equals negative 1/2 x squared plus 5x from the galactic coordinates 0, 0 to 8, 8 with both x and y given in parsecs. So in parsecs, what was the distance flown by the Falcon on this run? Okay, in parsecs, we need to find a distance formula. So I need the derivative. I'll need dy dx. dy dx is equal to the derivative with respect to x of negative 1/2 x squared plus 5x. That derivative is equal to negative x plus 5. So dy dx squared is just equal to negative x plus 5 whole thing squared. Now, the next part here is to set up the distance. So we usually call this arc length and not distance. So the arc length, that's going to be equal to the integral from x min, which is 0, to x max, which is 8, of root 1 plus negative x plus 5 squared dx. And that's the integral from a to b of 1 plus dy dx squared dx. Integrating that, again, you're supposed to just use your calculator. So chuck that into your calculator, and you should get 19.55640 parsecs, which, I don't know, good, bad, who knows. I also realized this is the same problem that we had just done earlier, so it's kind of funny that I went and I finished the problem beforehand. Anyways, if a typical Kessel run is 18 parsecs, was this particular run longer or shorter than typical? So this is longer than typical. By how many parsecs? 1.55640 parsecs. So that is arc length. A little bit easier than all of the area stuff that we've been doing. And it certainly, after you've gone through area, arc length just feels like nothing. So that's it for today, and we'll see you next time. Oh yeah, this is the end of your Chapter 8, so you should be getting ready for a Chapter 8 test soon. Make sure you check out the solutions that we're going to post online. Have a good one. See you next time. And good luck on your Chapter 8 test.